Hey guys, we are talking about metabolic pathways today. So going back to revisit chapter 3 and then concluding the recording with chapter 21. So metabolic pathways within cells and the whole body. So we are combining two chapters to complete the concept how the body handles nutrients, how the body makes macromolecules, and how the body breaks down macromolecules. So we'll be focusing on carbohydrates, proteins, and lipids. We're not going to talk about nucleic acids. So again, and then some of the carbohydrate, for example, catabolic pathways for glucose, we talked about that already. So we won't be repeating that. And also protein synthesis, we won't be repeating that. So only aspects where we haven't talked about for carbohydrates, we're going to talk about how the body basically produces carbohydrates because we handled glucose oxidation already. And for proteins, we're going to focus now on how the cells break down proteins. So with that said, we're going to go over this concept of metabolic pathways. So when we say, for example, let me annotate something here. When we say anabolism, we are talking about anabolic pathways. In other words, all chemical reactions used in the body to produce something more complicated. So from building blocks, for example, we start with amino acids, we build proteins, that's an anabolic pathway. If we start with glucose and when we produce glycogen, that's also anabolic pathway. If we start with glycerol and fatty acids and we build triglyceride, that's an anabolic pathway, right? So starting with simpler substrates to produce more complicated products, that's anabolic pathways. Chemical reactions catalyzed by enzymes to produce products that are more complicated than the starting substrates. And the opposite reactions are called catabolic pathways. So for catabolic pathways or catabolism, we are talking about, let's say we start with a macromolecule and we break that macromolecule down into its simpler constituents. For example, in a catabolic pathway, your starting substrate would be a protein, and your products would be released amino acids. So again, catalyzed by different enzymes. So enzymes come in and basically break down the protein and to release amino acids, right? Another example of catabolic pathway is you start with glycogen as your original substrate, starting substrate. With proper enzymes, you cut it down and to release glucose, monosaccharides. Again, that's an example of catabolic pathway. Chemical reactions to break down macromolecules into building blocks. Lipids, you start with the starting substrate, lipids, a macromolecule. With lipase, you generate glycerol backbone and fatty acids. Those are simpler constituents. That's another example of catabolic pathways. And when we say metabolism or metabolic pathways, we are talking about the sum of all anabolic pathways plus catabolic pathways. So when we say metabolism, we're talking about the entire set of all chemical reactions used to build, so anabolic chemical reactions, and chemical reactions used to break down, catabolic chemical reactions. So the sum of these both anabolic and catabolic reactions, we call them metabolism or metabolic pathways. So that's my quick review about the concept of metabolic pathways, including the sum of anabolic pathways and catabolic pathways. And with that said, we're going to go over specific pathways for how the cell produces carbohydrates. So glycogen formation. So focusing on the synthesis of carbohydrate, because break down glucose is underneath here. We already covered that. So this is catabolic pathway through, for example, aerobic cellular respiration. We covered that, so I'm not going to repeat that. We're going to also see how the cells generate lipids, so lipogenesis. And we're going to go over not protein synthesis. We covered that already, but when we talk about protein, we're going to focus on how protein will be break down. So protein catabolism, we're going to focus on that. Because protein anabolism, we already covered that too. Okay. So with that said, let's start the lecture. Now, glycogen metabolic pathways. This is a very, very important concept. So let's review here. We talk about this glucose moving through this pathway here, this arrow, becoming glucose 6-phosphate, and we go down and we get pyruvate. That's the pathway that we call that glycolysis. Right? So this occurs regardless whether the cell has oxygen or not. So you start with glucose, a 6-carbon compound, and you generate 2 3-carbon compound, pyruvic acid or pyruvate. And we learned that. So this is the pathway. And the only way for this pathway to occur, there's an enzyme here. That enzyme is very important. Hexokinase. Hexokinase means hexo is a 6-carbon sugar. Kinase is an enzyme that adds a phosphate, right? So hexokinase means this enzyme adds a phosphate group onto the glucose, more specifically onto the carbon at the 6th position within the glucose molecule. So that's why it says the substrate is glucose, the product is glucose 6-phosphate. So the phosphate group has been attached to the 6th carbon, carbon number 6 on the glucose skeleton. It's a 6-carbon glucose, so carbon number 6 on the glucose skeleton will receive that phosphate that has been added by hexokinase. Without hexokinase, the conversion of glucose into glucose 6-phosphate is not possible. And this is why is it important? Because without the glucose 6-phosphate, so this is a crossroad here. So without the glucose 6-phosphate, you will not have glycolysis. So this pathway here for glycolysis will not occur. So the cell needs to convert glucose into glucose 6-phosphate. Then we have a business going. So from glucose 6-phosphate, if you get the glucose 6-phosphate, then you can proceed glycolysis And if you have oxygen, then you would go into the Krebs cycle and electron transport chain to finish off the oxidation of glucose to generate ATP, right? Or you can go the opposite. So you can go from glucose 6-phosphate, if it's excess, you can form glycogen. So you can produce glycogen if you have glucose 6-phosphate. So you go this way. So you're storing excess glucose in the form of glycogen. So we call that glycogenesis. So genesis means producing, you're producing glycogen, right? So from glucose, you have to convert that into glucose 6-phosphate. And then you can store it as in the form of glycogen, or you can break it down by glycolysis to produce 2-pyruvic acid. And if the cell does have oxygen, each pyruvic acid will be decarboxylated into acetyl-CoA, and then acetyl-CoA goes into the Krebs cycle to generate these high energy electron carrier, and those high energy electron carrier go into electron transport chain through oxidative phosphorylation to get ATP. So a complete oxidation of the glucose. We learned that. So this is an important process. Hexokinase, a critical enzyme, okay? Hexokinase found in most body cells because most of the cells need the ability to oxidize glucose for energy. So in order for a cell to oxidize glucose to obtain energy, you need this pathway. You need the ability to get this pathway. I'm going to erase that. I'm going to be more specific than this. You really need to be able to do this. Yeah. So converting glucose into glucose 6-phosphate, and from there, you can store excess glucose into glycogen going on top, or you can oxidize glucose to get energy going to the bottom. So if you go to a pyruvic acid, you are oxidizing glucose, the process of kickstarting the oxidation of glucose to obtain energy, ATP. Or if you go up to glycogen, it means you're storing excess glucose in the form of glycogen. And then the opposite reaction is also important. And this is by another enzyme catalyzing the opposite, the reverse reaction, glucose 6-phosphatase. Phosphatase means an enzyme that cuts off a phosphate group from a substrate. So in this case, the glucose 6-phosphate has a phosphate on the 6th carbon. That phosphate would be hydrolyzed, taken off by the glucose 6-phosphatase to generate glucose. This is an important chemical reaction, and here's why. What's going to happen is glycogen is stored in the liver, right? So when glucose in your blood plasma drops, that drop in blood plasma is basically detected by the alpha cells of the pancreas, and the alpha cells will release a hormone called glucagon, and that hormone will use the bloodstream to go from the pancreas into the liver, inducing hepatocytes to break down glycogen, converting glycogen to break it down into glucose 6-phosphate. And then from glucose 6-phosphate, you go into glucose. And this glucose would eventually be released into the bloodstream, bringing blood plasma back up, right? So this happens between meals. We covered this. So this is basically tied on everything together. So between meals, your glucose concentration, the concentration of glucose in your blood plasma decreases, drops. That drop is detected by pancreatic cells, specifically the alpha type pancreatic cells. Once that they detect that, they release a hormone called glucagon into the bloodstream. Glucagon utilizing bloodstreams to go to the liver, activating hepatocytes or liver cells to hydrolyze glycogen to release glucose. Okay? In this case, glucose 6-phosphate, and the glucose 6-phosphate would be dephosphorylated by the glucose 6-phosphatase to release glucose into the bloodstream. So the body cells can pick up the glucose. So this is an important step too. So two enzymes, hexokinase and glucose 6-phosphatase. Hexokinase is expressed. This is a protein-based enzyme. So this protein, hexokinase, is expressed by most of the body cells. And the glucose phosphatase is also another type of protein, another protein-based enzyme. In this case here, the glucose 6-phosphatase is only expressed by liver cells, hepatocytes. Now, it happens also that, let's say, the body, the host or the individual decides not to eat any carbohydrates. So in his or her diet, this person is completely lacking carbohydrate intake. In other words, the person is not consuming any glucose, any glycogen, any starch, any disaccharides, no polysaccharides, no disaccharides, no monosaccharides. Complete zero carb intake. We have a problem. If that's the case, the body needs the ability to produce glucose and release that glucose into the bloodstream, because that glucose is required by neurons. Remember this at the beginning of the semester? I talked about this. Neurons will not, I repeat, will not rely on anything, only glucose as the only source of energy. The only type of fuel molecule that neurons can oxidize to obtain ATP is glucose. So if you don't consume carbohydrate, the body will use other building blocks to convert them into glucose. And this ability is because of chemical reactions are reversible. That's the beauty about chemistry. Chemical reactions, if you go from A to B, you should be able to come back from B to A, right? That's when we say reversible chemical reactions. And in chemistry, when we talk about reverse chemical reactions, you will see always, for example, substrate A plus substrate B come on, man. A substrate B. I'm going to use another color for clarity. So plus here, and you will produce A, B as a product, and you will have this direction, And you also will have the opposite direction. Okay. So the two arrows indicate the two reversible chemical reactions. A is a substrate, B is a substrate. So you start with two substrate in the green arrow, you produce AB product if you go through the green arrow. If you go through this orange arrow, I think it's orange, this AB becomes a substrate and A and B over here becomes a product. So depending on which direction you go, chemicals can be a substrate, but the same chemical becomes a product for the reversible, the opposite direction of the chemical reaction. Because of this concept, reversibility of chemical reactions, the body can basically start with amino acids and obtain glucose and vice versa. The body can start from glucose and produce lipids and vice versa, right? So that's the beauty about chemical reactions, being reversible, allowing cells to basically play around with different types of chemicals, different types of families of chemicals for life. So the family of carbohydrate, the family of lipids, the family of proteins, the family of nucleic acids. So within those families, the cells can use specific enzymes to basically break something down to produce something else and vice versa. So this is exactly what you're seeing here. You start out with triglyceride. So from triglyceride, you can break it down into the two constituents, the fatty acids and the glycerol backbone. So those are the two components of a triglyceride. Each triglyceride molecule consists of a glycerol backbone and 3 fatty acid molecules. And you can see here, if you start with glycerol using glycolysis, you can convert glycerol into pyruvic acid. And from pyruvic acid, you will go into acetyl-CoA, and then going down the Krebs cycle, oxidative phosphorylation to generate ATP, right? So you can use triglyceride to produce glycerol to convert it to pyruvic acid, and through cellular respiration, aerobic cellular respiration, you can obtain cellular energy, ATP. So you don't need, glucose in this case, right? And same thing with fatty acid. You can burn fatty acid. You can break down fatty acid and convert fatty acid into acetyl-CoA. And this acetyl-CoA, so fatty acid here, I'm going to change the color, becoming this acetyl-CoA. And this acetyl-CoA will go also through aerobic cellular respiration to get to generate cellular energy, ATP. Huh? And when we say glycolysis, we can also do reverse glycolysis to get glucose. So from glycerol, you go into glycolysis to produce pyruvic acid, but also using pyruvic acid here, you go reverse glycolysis to produce glucose. So this is for neuron consumption. And you see a beauty here. So in this case, you start with a protein. You break down protein to obtain glucose. Or you can break down protein, Krebs cycle, instead of going here reverse glycolysis, you go straight down through the rest of aerobic cellular respiration to get ATP down here. This is also how you break down protein to get energy. You never want to do this, guys. Okay, you don't want your cells to break down your proteins to obtain energy. This means you are under stress. This means your body sees an event as a traumatic event. So let's say, for example, starvation. If you starve yourself to lose weight doing the wrong way, this is what happens. Instead of burning fat, your body stores more fat. The body will break down your muscles to get energy. So you're losing muscle mass instead of burning fat to obtain energy. So this is the wrong way to, losing weight, right? So this is truly a case where no pain, no gain. You want to lose weight by burning fat, you need to exercise. You need to eat less. So any program of losing weight is 80% of it depends on what you eat, depending on your calorie intake. To lose weight, you do it slowly over a long period of time by having a deficit of caloric intake, meaning if you need 2,000 calories a day, you intake only 1,500 a day. So you're basically forcing your body to in deficit, meaning you take 500 calories less than what your body requires. If you do that consistently with a balanced meal, right? But only taking 500 calories less than what your body requires based on your weight, you will lose weight the healthy way. It takes longer, but you will lose weight. The very least, you will lose around 1 pound of fat per week if you follow that regimen. You don't need to exercise. Now, you eat properly, eat a healthy, balanced diet with all the groups in your food. Just make sure that you are basically taking in 500 calories less than what you need. And you will see a weight loss, long-term sustained weight loss, the healthy way. And in that case, you're not breaking down your proteins, but you will burn the fat. Okay, so this slide here is to show you the principle is very simple. When we say gluconeogenesis, gluco means glucose. Neo means new. And genesis means to generate, to produce. So you are producing new glucose, meaning you're producing glucose with starting substrate being non-carbohydrate source, right? So you are producing glucose with starting substrates coming from lipid, for example, glycerol or amino acids to generate glucose. This happens for two reasons. Number one, like I said, the patient, the individual is not taking there's no intake of carbohydrate. There's no monosaccharide intake. There's no disaccharide intake. There's no polysaccharide intake in his or her diet. If that's the case, the body still needs to generate glucose for neuron consumption. And the body will rely on the concept of reversibility in chemical reactions to use non-carbohydrate substrates to produce glucose. It's such a beautiful concept. It's such a beautiful application of one of the fundamental sciences, in this case chemistry, and apply that to life, biology. Moving on to the next one. Anabolic pathways for lipids, the same concept. You can start with something completely new. So let's say you eat an excess of glucose. So you have excess of, so if you have excess of glucose here, you can go this pathway, and this is the danger here. This glucose will use this pathway. This glucose will you go all the way down here. From acetyl-CoA goes up here. Right? So from glucose, you can generate glycerol, or you can generate fatty acid, and combining the two, you are producing excess fat, and that will be stored in your adipose tissue. So this is the conversion of excess glucose into triglyceride. So this is why we gain weight when we eat excessive carbohydrate. That's the pathway. And that's why you see most of these chemical reactions are reversible. They go in opposite direction. So in other words, it's shown here clearly, glucose can be converted into glycerol by this pathway, or glycerol can be converted back to glucose by this pathway. So that's the reversibility concept I keep repeating because it's important. Okay, now, one thing though, this is due to the way the body's building fatty acids. The acetyl-CoA, it's a 2-carbon substrate. And that same acetyl-CoA will be used to build fatty acids by this arrow. Okay, from fatty acid to acetyl-CoA to fatty acid. Because of that, fatty acids in our cells are always have an even number of carbon. So we can have only like fatty acid that is 10 carbon, 12 carbon, 14 carbon, 16 carbon, 18 carbon, 20 carbon, 22 carbon, so on and so forth. We cannot have an odd number of carbon because the building blocks of fatty acids in human cells are based on the acetyl-CoA 2-carbon subunit. Okay. The acetyl moiety in the acetyl-CoA coenzyme A. So because of that, fatty acids in our cells are always have an even number of carbon. It's not possible to have an odd number. It's not possible to have a fatty acid with 9 amino acids. It's not possible to have a fatty acids with 11 amino acids. It's only even numbers, right? 2, 4, 6, 8, 10, 12, so on and so forth, but not odd numbers because of this fact. So this is like a building block for fatty acid formation based on a 2-carbon substrate. So you add 2 carbon at a time, from 2 to 4 to 6 to 8 to 10, and so on and so forth. The opposite reaction is also important. It's called beta oxidation. This is when we break down fatty acid to generate acyl-CoA, and that acyl-CoA goes into the Krebs cycle and goes out for the rest of the way, aerobic cell respiration, to get cellular energy. And this is the best way to get energy. Fatty acid is the best type of molecule to store energy because they are hydrocarbons. They consist of carbon and hydrogen. We call them hydrocarbons. This is the essence of gasoline as well. So all fossil fuel are basically energy stored in hydrocarbons, including gas that you put in your car. That's hydrocarbon, right? So that's the best way for chemistry to offer for storing energy for use by life forms. So all fossil fuels are hydrocarbon based, including in this case fatty acids. So when you break down fatty acids, you generate much more energy than when you break down carbohydrates. So for example, a one single fatty acid molecule, let's say a C14, C16 with 16 carbons, would generate around 130 ATP molecule. So much more capability to store energy. And also on top of that, it's lighter weight. So this is why nature chose fat to store energy. This is why we gain weight, not by storing excess sugar, but by storing excess fat. Because if nature chose carbohydrate for us to store energy, we wouldn't weigh 100 pounds or 150 pounds. We would weigh like 3-4 times heavier because sugar is much more heavier than triglyceride, than adipose, than lipids, right? So this is why nature chose lipids to store energy, more specifically triglyceride. They have a lighter weight compared to carbohydrate, but they also store much more energy than carbohydrate. So you can also use proteins to generate amino acids. And some of the amino acids can be converted into pyruvic acid or go straight into the acyl-CoA, becoming acyl-CoA, so 2 carbon. And then from here, you can go into the acyl-CoA, into the rest of the aerobic cellular respiration pathway to get ATP. So you can start with proteins to obtain cellular energy. You can obviously start glucose, we learned that. But now today, we also know that you can break down oxidized triglyceride to obtain cellular energy. So if you start with triglyceride, you can use glycerol, and glycerol has to go into glycolysis to go down, or fatty acid, go straight into acyl-CoA and go down, right? So this pathway that we learned earlier in the semester, glycolysis, decarboxylation to generate acyl-CoA, going to the citric acid cycle, electron transport chain to obtain ATP. That pathway is not only used to oxidize glucose, which is a monosaccharide, but it's also used to oxidize other building blocks of other families of macromolecules. Proteins in this case, triglycerides in this case. So this is central pathway to oxidize the substrate. It doesn't have to be carbohydrate to get ATP, cellular energy. We also use the same pathway from acyl-CoA. You can use acyl-CoA to produce cholesterol. And this is important here. It doesn't matter whether you intake cholesterol or not. The body always produces cholesterol because cholesterol, it only shows two functions here. Cholesterol is used as a building block to produce steroid hormones. We learned that as well. So the adrenal cortices and the gonads are using cholesterol as building blocks, starting material, substrates to produce all three families of steroid hormones. Cholesterol is also used as a building block to produce bile salts, to emulsify fat from our diet. So to basically allowing lipase in the luminal space in your GI tract to have more access to lipids, to kickstart breaking down lipids. So bile salts would basically use to break down larger fat globules into smaller globules, so increasing surface area contact for lipase to facilitate lipid digestion. And those bile salts are basically built from starting material cholesterol. There's another important function of cholesterol not shown here, but we mentioned that at the very beginning of the semester, and that's basically providing stability to the cell or plasma membrane, right? So cholesterol providing stability in the cell membrane, in, for example, during when the temperature increases, the presence of cholesterol in the plasma membrane or cell membrane prevents that membrane from melting, prevents that membrane from liquefying. And when the temperature drops, becoming colder, the presence of cholesterol in the phospholipid bilayer prevents that phospholipid bilayer, prevents a cell membrane, prevents a plasma membrane from freezing. So that cholesterol is also important for maintaining the integrity of the three-dimensional structure of that membrane, that boundary, right? Cell membrane, plasma membrane, phospholipid bilayer, you name it. And in those, that structure contains lots and lots and lots of cholesterol used as small, tiny wedges between the phospholipids and the membrane proteins, providing stability to that structure, to the cell membrane, plasma membrane, or phospholipid bilayers. And what else? Ketone bodies, there you go. So fatty acid here can basically convert into ketone bodies, and these ketone bodies can also convert it to acyl-CoA and get that energy. And ketogenesis means basically the conversion of fatty acids into a form of amino acid, not really amino acids, just acids that are basically lacking the amino group. We'll talk about them later in the lecture about this, but the point here is ketone bodies, if you generate them, they are used also as a substrate to produce cellular energy. So they would have to go and convert it into the 2-carbon acetyl-CoA, and then from acetyl-CoA as a substrate into the citric acid cycle, electron transport chain, and getting that cellular energy. Ketogenesis. Genesis means to produce, to generate. Keto means ketone bodies or keto acids. Now moving on to lipid. So we learned briefly about this one here, lipolysis, catalyzed by lipases. So from triglyceride, you generate glycerol and 3 fatty acids. And this is why we say, if you want to burn fat, you exercise, because when you exercise, you are activating your sympathetic division. And this sympathetic division, when you activate the sympathetic division, you basically inducing breakdown of triglyceride to release fatty acid, because the fatty acid then will be used to generate cellular energy through the pathway that we learned earlier today, right? So this is the best way. This is the only way to burn triglyceride. Is for whatever reason, somehow you activate your sympathetic division, your fight or flight division. And the only way to the healthy way to activate this is through exercise, vigorous exercise. So when you do vigorous exercise, you're activating, you're turning on your sympathetic division. And once that division, that autonomic division of our motor system is activated, it will drive, it will burn, it will convert, it will break down triglyceride into glycerol and fatty acids. And ultimately, the released fatty acids would be oxidized to produce cellular energy. This is the healthy way to burn that fat, to shed that fat away from your body if you have excess fat. Okay, so 2 things: eat sensibly, make sure that you have a caloric intake deficit, and exercise. Not only you're basically helping your body to burn that fat, but also you maintaining your cardiovascular health. So the more you exercise, it benefits your heart. It clears your pipes, meaning your vascular beds, right? And it makes you feel good too. So increased dopamine release, that makes you feel good. So that's our natural high, if you will, that exercise. No, truly no pain, no gain, guys. Okay. And then we talk about this beta oxidation of fatty acids. So the coenzyme to the 2 carbon fragments from the acyl CoA, beta oxidation, Krebs cycle, and East electron transport chain. So it follows this. So for example, like I mentioned earlier, a 16 carbon fatty acid would generate 130 ATP molecules. Okay. So it's much more energy than carbohydrate storage. So this 16 carbon fatty acid, which has a name, palmitic acid, it's also lighter. So if you have a corresponding 16 carbon sugar, it would weigh much more than a 16 carbon fatty acid. That's what I meant when I say weight-wise, mass-wise. So for the same mass between the two, a fatty acid and a carbohydrate, the carbohydrate always stores less energy than a corresponding mass of fatty acids. And this is an important concept, right? So the reason is because fatty acids is a derivative or the same family of hydrocarbons seen in fossil fuel. And we all know fossil fuels we are burning fossil fuel to get our energy, including the gas in our cars. So this is kind of a summary here showing you the three families of macromolecule: protein, polysaccharide, carbohydrate, and one form of lipid, triglyceride, right? So look at the power of these reversible chemical reactions. But what is important is, I'm going to highlight this with another color. Oops. Sorry, guys. I have to redo this. So that's the pathway that we already learned. Aerobic cellular respiration, meaning cellular respiration in the presence of oxygen. Okay. So whatever substrate are you talking about? So this is the difference here. We take it to another level here. Is we only talk about glucose. So with glucose, we follow this pathway in red to get ATP. Today, what is new is, in addition to glucose, we know that this process can also take amino acids, can also take glycerol and fatty acid. They might enter the pathway at different location, but it is still applicable. That's the beauty about it. So glucose enters on top of glycolysis. Glycerol enters on the side of glycolysis here. Fatty acid enters the cycle, becoming acyl-CoA. Amino acid, before they can be used, they need to have their, let me use another color, amino group here taken out. And we'll talk about this later. So amino acid that has the amino group taken out, we call that the keto acid. And we'll talk about that. So once that amino acid has been taken out, then it can go into becoming a pyruvate. It can be converted into acyl-CoA, or it can go straight into that Krebs cycle. So I'm going to write 3 clear arrow in red here so you can see. So once this happens, done, amino acid loses the amino group, it can be converted into pyruvate. It can be converted into acyl-CoA, or it can go into the Krebs cycle, depending on the type of amino acids, right? It can go into either 3 of them. The point is, it can be used to obtain ATP. The same thing over here, glycerol can go into glycolysis, or fatty acid can go into the acyl-CoA, or much later into the after the Krebs cycle and straight into oxidative phosphorylation for fatty acids. Now, so that's what is important, is not only you using this pathway to obtain cellular energy. So starting with different substrate. So you start with amino acid, you can get ATP. Starting with glucose, you can get ATP. Starting with glycerol, you can get ATP. Starting with fatty acid, you can get ATP. So that's the catabolic pathway. Now, I'm going to talk about the opposite now, anabolic pathway, right? Now, what if the individual is not, intaking any carbohydrate? So there's no polysaccharide, no disaccharide, no monosaccharide, no glucose. So we learned earlier, the body can break down protein to get to glucose. So what we have is you follow this pathway. This amino acid will lose the ammonia, the amino group, and keeps going, converts into pyruvate, and it will go up. If it goes up, that arrow is called reverse glycolysis. So pyruvic acid becoming converted to glucose, and that glucose is for brain consumption, for neurons. Okay. Same thing with triglyceride. The body can basically convert triglyceride into glucose for neuron consumption. So you go, it breaks down to glycerol. So if it's glycerol, it goes this way and then up. Or fatty acid, it goes down here. Acyl-CoA, we have a problem. We down here, we have a problem. So the only way, and this is mentioned here, the only way for triglyceride to generate glucose is from glycerol. Because fatty acids, they go, for example, here. If you look closely, fatty acid goes here, acyl-CoA, there's no arrow coming back up. So this arrow is pretty unique. It's irreversible. So from pyruvic acid, it converts to acyl-CoA, and that's irreversible. So if it becomes acyl-CoA, it cannot go back to pyruvic acid. Okay? It needs to go the long route. So fatty acid, acyl-CoA, becoming amino acid, and then going back this way, which is basically very hard to follow. So whenever the body needs glucose, the easiest way is break down protein to get glucose. And the reason is, at this moment, the body sees that as a traumatic event. It will save, it will store. It won't touch the triglyceride. On top of that, it breaks down protein, and if it keeps going long term, it will also force the body to break down protein and to store triglycerides, so to produce fat as well. Because when you're eating, you're not only eating protein, you're eating lipids. So all that excess lipid that you're eating in will be converted to triglyceride, whereas the protein that you're eating will be converted to glucose. So either way, you're not basically burning the fat. You're actually saving that fat, right? So the trick here again is to make sure that you have a deficit in caloric intake. That's why the protein diet works, is because when you eat the protein, you're basically forcing your body to break down the protein to produce the glucose. And long term, if you have a caloric intake deficit, then the body will basically induce triglyceride burning as well to produce energy, and also burning that fatty acid to produce cellular energy. Okay. But the problem with the protein diet, the irony is the person who basically founded that diet ultimately died of cardiovascular disease. So we have, I don't believe that we have direct experiment evidence, but we have inconclusive data hinting that if you eat that protein-based diet long-term basis, you might have problems in your cardiovascular system. On top of that, if you have genetically basis of having, for example, high cholesterol, then you're exacerbating the problem. Okay? So the proper way is just eat a healthy, balanced diet, protein in your food, carbohydrate in your food, triglyceride in your food, and also vegetables in your food, and exercise. Make sure that you eat less than you need, and a long term you will lose that weight if weight loss is important to you. Now, this is the keto acid I'm talking about. Some amino acids, there are 20 amino acids used to build proteins. And the essential amino acids have to be obtained from food. And when the amino acids that can be produced by the body, they are called non-essential amino acids. And if you look closely here, this is the amino acid. Transamination means hepatocytes can catalyze this, meaning this amino acid will give its amino group to the keto acid. Right? So this amino acid now becomes a keto acid that I mentioned earlier. So keto acid means it's an acid, it's an amino acid without its amino group, right? And then the keto acid receiving that amino group becomes the glutamate or glutamic acid. And hepatocyte can basically cut off that amino group and it becomes ammonia. And ammonia is very toxic. So hepatocyte will bind carbon dioxide to ammonia to produce urea. And this urea will be handled by your kidneys and excreted in urine. Okay, so it's a waste product, catabolic waste product coming from protein. So when we break down protein, we generate lots and lots of acidic byproducts. The most important of them is being urea. Okay? And we learn that from the urinary system, that urea can also be used to help the juxtamedullary nephron to concentrate on urine. So urea is not only a waste product, but it can also be recycled for a purpose. Okay. So this is important. In order for the body to use amino acid as a substrate to generate glucose or to burn down that amino acid to obtain energy, that amino acid needs to have its amino group removed and becoming a keto acid. So keto acid then can be used to produce glucose, or the keto acid can be used as a substrate to generate cellular energy by relying on the aerobic cellular respiration pathway that we learned earlier. So that amino group needs to be removed before the body can use that keto acid as a substrate. And then here is the opposite, protein synthesis. We talked about this already. So gene expression means protein synthesis, protein production, and protein synthesis includes two steps: transcription and translation. And we learned all of that, so I'm not going to go back and repeat myself here, because I consider that you're expert in the concept of protein synthesis by now. Now, so what happens when we break down protein? We learn about protein synthesis. Let's focus on how do we break down proteins. This is under stress, long-term stress. Cortisol is a stress hormone, so it's a steroid hormone produced by the adrenal cortex. So long-term stress, like for example, traumatic tissue injury or sickness, right? So it will drive amino acid release. Starvation, the same thing. You're not eating, so it drives amino acid release, and the amino acid release would basically, and this is the irony. The amino acid will basically use to produce fatty acid, and the fatty acid will be converted into triglyceride. So a neutral fat, right? So fatty acid will be combined to glycerol to produce the triglyceride, and triglyceride, we learned that is as a neutral fat. The amino acid can also be used to produce glucose. This is for neuron consumption. This happens also when you are not intaking any carbohydrate, right? So what happens here is you are forcing your body to break down your skeletal muscles. And when your skeletal muscles are broken down, this is a no point of return. This is irreversible, right? So skeletal muscles, this is one of the tissues where it's so differentiated, so specialized, they have lost the ability to regenerate themselves. So skeletal muscle fibers do not have the ability to generate new skeletal muscle fibers. So once you destroy them by using amino acids to get energy or to produce fat, then they're gone forever. So you're losing your muscle mass, right? So you're gonna say, what happens? Well, I see bodies, guys bulking up or girls, becoming bigger. They're not producing new skeletal muscle fibers. They are making the existing skeletal muscle fibers becoming bigger by producing more contractile proteins. That's a different thing. So the skeletal muscle fibers, each skeletal muscle cell can produce more proteins, like more myosin, more actin. But the cells themselves, you cannot produce new skeletal muscle cells. They're gone. If they're gone forever, right? So this falls under the domain of you have a catch here. You become specialized, you lose the ability to generate yourself. So cardiac muscle, skeletal muscle, neurons, they're so specialized in terms of functionality, they have lost the ability to divide. They cannot regenerate themselves. Okay? So that's the danger of breaking down proteins for energy, to generate energy or to generate glucose for neuron consumption. And the irony is, let's say you're starving yourself, you want to burn that fat. You're not burning the fat, you're actually producing more fat at the expense of your muscles. And then down here, if you're using amino acids to produce ATP, some amino acids, like for example, methionine and cysteine are two examples of amino acids that having a sulfur group. And that sulfur group needs to be released, needs to be get rid of before you can use that amino acid. And that's step number one. If it's methionine and cysteine, if there's no methionine and cysteine, you don't need to do this sulfur release step, okay? The sulfur release step only applies to methionine and cysteine. All other 18 amino acids go straight to this step here, deamination, removing of the amino group. And it becomes a keto acid. And once that happens, then the keto acid can be used to oxidize to generate ATP. So oxidation amino acid here, it should have been keto acid because it no longer contains the amino group. Okay? And that by going into the Krebs cycle electron transport chain to get that ATP. So that's the power of reversible chemical reaction. You can break down protein to generate amino acids. Once you have that amino acid, you can induce them to produce lipids, more specifically triglyceride, or you can get ATP, right? And this, before you get to ATP, you have to get glucose and then allow your neurons to get ATP. Okay. So this is again another summary here, the relationship between protein and glucose. So if you start out with the pyruvate here, and you're going up like this, and from glycolysis, you go into glucose. This arrow is called reverse. Glycolysis, okay? So why did I start with pyruvate? It's because of this, the protein. So this glucose here is for neuron consumption because you don't have any carbohydrate intake, right? So in your diet, you don't have polysaccharides, you don't have disaccharides, you don't have monosaccharides. None of the monosaccharides. You have nothing, completely no carb intake. So in your diet, you have proteins, hopefully. So the protein can come from your diet or can come from your skeletal muscles. So they will be broken down into amino acids. From the amino acids, the amino group has been taken out, converted into urea by adding another carbon dioxide. Once that amino acid loses its amino group, it becomes a keto acid. So this is a usable substrate. Okay. That keto acid can be converted into pyruvic acid. And pyruvic acid goes up into glycolysis instead of going down, and reverse glycolysis produces glucose. Or the same keto acid, instead of going to the blue arrow, it will go converting acetyl-CoA. It goes straight down for ATP production. right? Or it can go straight into Krebs cycle for ATP production, so energy production, right? So when you don't have glucose, carbohydrate in your diet, the body, to maintain homeostasis, it will be at the expense of your skeletal muscles. The proteins in your skeletal muscle fiber will be broken down, will be releasing amino acids, and amino acid will be, the amino group will be taken out, becoming the substrate, the usable substrate, keto acids. And from there, the keto acids can go to two routes. One, converted into glucose for neuron consumption. The other route, pathway, is to go straight down using aerobic cellular respiration, different steps, so to get that cellular ATP to remain alive, despite the fact that you don't have any carbohydrate in your food or diet. Again, all of this is possible because of the chemical reactions being reversible. But what is important is, I saved that for last because I want you to remember this, is all of these reversibility reactions is one pathway that is not reversible. So when pyruvic acid, this is a 3-carbon compound being decarboxylated into 2-carbon compound. That decarboxylation reaction is one direction and one direction only. It goes from pyruvic acid, 3-carbon, into a 2-carbon compound. It cannot go back. The reason is there's no enzyme. Our cells do not have that enzyme, that protein that can catalyze the reverse reaction, right? So because of that, once decarboxylation occurs, the acetyl-CoA will basically go straight into the Krebs cycle. And from the Krebs cycle, it will generate high energy electron carriers, NADH and FADH2. And these high energy electron carriers will go into the inner membrane of the mitochondrion, the electron transport chain, to basically convert all this energy into a storage form that we call ATP, right? So that's an important concept. So from the pyruvic acid into acetyl-CoA, once pyruvic acid is being decarboxylated, meaning it loses one carbon dioxide. This is the very first carbon dioxide that you're breathing out. It's produced by the decarboxylation step. The other carbon dioxide is coming from the Krebs cycle, right? So, but that decarboxylation step is irreversible. It cannot go back. Everything else is reversible. Also, the Krebs cycle, when you get into the Krebs cycle, if you look closely, all these arrows are one direction and one direction only. So when you enter the cycle, they are also irreversible. It's always unidirectional, okay? Same thing with the electron transport chain. You cannot go back, right? So what you can do is glycolysis is friendly because you can get in and get out of glycolysis. You can go glycolysis or you can do reverse glycolysis. Same thing here, the conversion of these different macromolecules into the building blocks, they are reversible. But the decarboxylation, the Krebs cycle, and the electron transport chain, those are irreversible. This is crucial as concepts because those are the pathway that when you get in, it's a domino effect. There's no going back because you will end up with ATP. This is nature's way of making sure that the cell always obtains ATP. Once you get the desired substrate for these steps, decarboxylation, citric acid cycle, electron transport chain, there's no point of return. You will go toward ATP production. That's important. Before that, who cares, right? I'm open. You can interconvert whatever you want, between different Lego blocks, building blocks. You can convert proteins to carbohydrates back to protein, or carbohydrate, you go into lipids and triglycerides, and vice versa. From triglyceride, you can become carbohydrates. But once you leave glycolysis and you enter decarboxylation, you enter citric acid cycle, no way of going back. You will go into the electron transport chain and you will obtain ATP. Now, moving on to chapter 21, we apply that for the entire body, the whole body. So we're gonna go over, we're gonna focusing on, let me move this out of the way. We'll be focusing on only here due to time constraint. So absorptive and post-absorptive state, we're not gonna go over this. And we will not be going this either. I just wanna mention here, and I think we talked about this at the beginning of the semester, the very important concept of energy. You cannot create new energy. You cannot destroy energy. You can only convert energy from one form into another form, right? For example, you can convert kinetic energy into potential energy, or you can convert potential energy back to kinetic energy, but you cannot create new energy. Energy is already there for us to use. And there's a price to pay when you convert energy from one form to another form. Every time you convert energy from one form to another form, you generate heat, H-E-A-T. That heat is also a type of energy. Unfortunately, for life forms, heat is a form of energy that is useless to drive life. So life cannot use that heat to basically harvest, to maintain homeostasis, right? So every time, so Mother Nature taxes us. Every time we convert one form of energy to the next, she's taxing us up to 60% taxation. So we get only 40% of usable energy every time. So for out of every dollar, Mother Nature takes 60 cents and lets us only 40 cents remaining to spend every time. Okay? That's how nature works, right? So that's the concept of energy I wanted to remind everyone that we already covered at the beginning of the semester. So that's just a quick review about it before we talk about what is absorptive state and post-absorptive state. Now this is happens when right during the meal or right after a meal. So we call it absorptive state. So what happened is when you're eating, or right after when you're eating, your blood glucose increase. So the concentration of glucose in your bloodstream increases. That increase in blood plasma glucose is detected by pancreatic cells. The 1% of all pancreatic cells, only 1%, 99% of them have digestive functions. But only 1%, among the 1% of pancreatic cells, there's one specific type called beta cells, or the pancreas, or beta pancreatic cells. They are sensitive to glucose in our blood plasma. And once they detect that, they are induced to release insulin into the bloodstream. When insulin, in this case, is a chemical messenger functioning as a hormone. So in this case here, the pancreas is producing hormones. So this is the endocrine function of the pancreas. Only 1% of all pancreatic cells have endocrine functions. 99% of the remaining pancreatic cells have digestive functions, right? So once insulin is released into the bloodstream, this chemical messenger using the bloodstream, your blood vessels, to have access to get distributed throughout every single systemic body cells. And once insulin shows up at the systemic body cells, they allow systemic body cells to absorb, to pick up, to take up glucose. And once body cells absorb the glucose concentration in your blood plasma decreases. So this happens every time that you're eating, right? This is during a meal or right after a meal. We call that absorptive state. So this is very straightforward. So you're going to do this on your own here. So this is what happens to most tissues. So the arrow that goes up means increase. The arrow that goes down means decrease. That's that. Let's move on to the next slide. This is very interesting. This is the molecular mechanism, allowing us to understand as to how insulin gets released. And this is done by the beta cells. So this you see here, this is a beta cells in the pancreas. So you have glucose concentration extremely high in the vascular bed. And this is right after a meal. And we have here a form of facilitated transport. This is a GLUT2 means glucose transporter, right? So facilitated diffusion driven by concentration gradient, no energy required. So high glucose would be transported by glucose transporter 2. And they are transmembrane protein located at the cell membrane, the plasma membrane of the beta cells in the pancreas. And once glucose gets in, it follows, the breakdown through aerobic cellular respiration, and it produces ATP, right? Now, what is interesting here, and this is new to you, is ATP in this case is used as a chemical messenger. ATP will basically bind to a transmembrane protein. And this transmembrane protein is an ion channel. But ATP binds to the protein not on the extracellular side. It binds to the protein on the intracellular side, right? So when ATP binds to this transmembrane protein, which is an ion channel, fluxing exclusively potassium cations. So when ATP is not binding, this channel allows potassium efflux, allows potassium to leave the cell, right? So when ATP binds to it, because ATP was produced by incoming glucose, when ATP binds to this potassium channel, it closes the potassium channel. So that's why it's called ATP selective potassium channel. So when upon ATP binding, the channel closes. Potassium cannot get out of the cell. What happens? Potassium accumulates on the inner leaflet of the cell. So it causes an accumulation of positive charge on the inner side of the membrane compared to the outer side of the membrane. And we learned this. It's a depolarization signal. So when ATP comes into the beta cells of the pancreas, the beta cell oxidize glucose to produce excess ATP. When we have an excess ATP, ATP binds to ATP selective potassium channel, close down the channel, potassium cations accumulate on the inner leaflet of the phospholipid bilayer of these beta cells, inducing the membrane to depolarize. And when the membrane depolarizes, it will activate voltage sensitive calcium channel, also present on the plasma membrane of these beta cells of the pancreas. And once these voltage sensitive calcium channels are opened by the membrane depolarization, calcium gets in, a massive calcium influx, as shown by the black arrow here. And once that massive calcium influx gets inside the beta pancreatic cells, it induces the vesicles containing insulin to fuse with the cell membrane and to release its content into the outside world. So in other words, these vesicles release insulin by exocytosis into the external world. And the insulin will use the blood vessels to get to the body cells, systemic body cells, helping systemic body cells to absorb glucose. So this is an important mechanism that you need to understand about it. Okay, I'm not playing games with you. This was basically during a face-to-face final was one of the topic for the essay during a face-to-face final. I think from 2 or 3 semesters ago. So make sure that you can understand the concept. Most of it is already, it's just an application of a concept that we already learned. So that's the beauty at this point is we go over the foundation of all of the molecular concepts. So just applications for you to appreciate. And this is just a negative feedback. Let me see if, yeah. So when plasma glucose increase, so this one here is during mealtime. So during a meal or right after a meal. So plasma glucose, so the concentration of glucose in blood plasma increase. Beta cells detects that and releases insulin, and you can learn the rest, right? So this is straightforward. So once insulin is released, it allows glucose to absorb, body cells, systemic body cells absorb glucose. And if you have excess glucose, you induce storage of glucose in the form of glycogen synthesis. And then once you have excess glucose, you don't want to cut glycogen. So you drop the glycogenolysis here, meaning this is basically when glycogen is hydrolyzed to release glucose, so that decreases. And you also decrease the gluconeogenesis by the liver, meaning you're basically not allowing the liver to produce glucose by breaking down proteins, right? So it makes sense. So you can learn that on your own. There's nothing cerebral there. Now, if we have absorptive state, we also have post-absorptive state, meaning this is what happens when we are not eating between meals, right? So we call that post-absorptive state. So what happens between meals, like between breakfast and lunch, or between lunch and dinner, or between dinner the night before and breakfast the next morning, you don't have glucose intake. So the concentration of glucose in your bloodstream will drop, will decrease. Once that happens, another type of cells, this is also part of that 1% endocrine cells of the pancreas. And this time here, it's called alpha cells or alpha pancreatic cells. They are sensitive to a drop in the concentration of glucose in our bloodstream. bloodstream. And once that happens, they release another hormone, not insulin, they release glucagon, right? So that's another chemical messenger released into the bloodstream. So glucagon here also is an endocrine chemical messenger, aka hormone. And glucagon will basically induce the liver hepatocyte to break down glycogen to release glucose into the bloodstream. Okay. So glycogenolysis, meaning breaking down glycogen to release glucose into the bloodstream, to bring that blood glucose concentration back to homeostasis. Okay, so the rest you can learn that on your own, but that's the main point is when between meals, blood glucose drops, glucagon release goes to the liver and induces the liver to hydrolyze glycogen to release glucose into the bloodstream so that the body cells can absorb that glucose, especially maintaining glucose within the homeostatic window so neurons can have access to glucose. And this is kind of the same thing here. So plasma glucose drops, alpha cells in the pancreas detects that, releases glucagon in response. And these are the responses, bringing back homeostasis based on negative feedback mechanism. So I think that's the last slide of the lecture. So on that note, I will end the recording today, and then I will see you for another one before the semester officially ends on Wednesday. So on Wednesday, or the next recording, sorry, will be the last one, and that's pertaining to the physiology of reproductive system. Until then, stay safe, stay healthy, be happy, and we'll talk to each other soon. Take care. Bye.